Hi everybody and welcome back. So today we're going to talk about free fall. And we saw in some of the examples and demonstrations that we did in class that if we were able to ignore or remove the effect of air resistance on an object, that all objects would fall with the same rate of acceleration. So I want to talk about why that is for a second. So if we could take away air resistance and you take an object and you drop it, the only force that would be acting on it in that case would be gravity. And gravity is a constant force. It doesn't change how hard it pulls. All right, it pulls with the same amount of force on a particular object. All right, so that force is going to cause a constant acceleration or a uniform acceleration on an object. So if we were able to take a hammer and a feather and put them in a situation where there was no air and we dropped them on Earth, they would both fall at exactly the same rate. So we can demonstrate how this works in class by, taking a piece of paper and a textbook and dropping them, and we see that they fall differently. But if we crumple up the paper and we drop it again, we notice that the paper falls a lot faster. Well, it's not because the force of gravity has changed, it's because by crumpling up the paper, we have minimized the effect that air resistance has on that object. We could do it another way by getting a tube, a vacuum tube, where we have no air inside the tube, and we can drop things like little bits of paper and a coin, and we can see that they fall at exactly the same rate. So gravity causes the same acceleration on all objects. That's the number one fact that we need to know. So when we talk about free fall, a freely falling object is any object moving freely under the influence of gravity alone. So if gravity is the only force acting on it, then it's in free fall. Now, there might be some situations where that makes perfect sense to us, and there might be some other situations where that's kind of confusing. So let's kind of talk about that. So most people think of free fall as I take an object and I drop it, that's free fall. And you're not wrong, that would be true. If I let this thing go and just let it drop down, gravity's acting on it, it's in free fall. But what we might not think is free fall would be if I tossed an object up in the air. Most people don't consider that as free fall. Most people that are not physics students don't think of that as free fall. Or if I take an object and throw it downwards, like I was spiking it or something like that. Most people don't think of that as free fall either. But all three of these examples, dropped or thrown downward or thrown upward, are all examples of free fall in a physics sense. And here's the main reason why, and this is what you need to get. Regardless of whether I drop it, throw it up in the air, throw it downwards, in all three of those cases, the only force acting on it once I let go of it is gravity. We're not talking about like as I'm in the process of throwing it or as I'm in the process of launching it upwards, but once I let go of it. If I let go of it, once I let go, just gravity acting on it. Same thing if I toss it up, same thing if I toss it down. So all of these are examples of free fall, and that's a super important thing for us to understand. Okay, next. If an object's in free fall, then the acceleration of the object is directed downwards. And you notice I highlighted and said all the time. Okay, if it's in free fall, its acceleration is going to be in the downwards direction. Why? Because gravity is acting on it, and gravity is a downwards force. It causes a downwards acceleration. Don't get into the habit of saying, well, what if I throw it up in the air? Well, it's still in free fall. Gravity's still the only force acting on it. The acceleration of that object is downward. We want to make sure that we don't get confused between what's the velocity of the object and what's the acceleration of an object. We can have an object that's moving in the upwards direction, but have a downwards acceleration, remember. Because the fact that it's moving upwards just means it has an upwards velocity, not necessarily an upwards acceleration. The acceleration is going to be in this direction. And the amount or the magnitude of the acceleration is 9.8 meters per second squared. And we use the symbol lowercase g here for the gravitational acceleration. So you're going to see that symbol a lot. When we write down that little g, we mean the acceleration due to gravity is 9.8 meters per second squared in a downwards direction. Okay, so when we talk about free fall, we are first of all neglecting air resistance. We're ignoring any effect of air resistance. And the main reason for that, there's two actually. So the first is that for a lot of objects, the amount of air resistance that act on them as they move through the air is so small that it's negligible. We don't have to worry about it. It's not really going to change our results very much. Okay. Now, there are some exceptions to that. If you drop like a feather, all right, or an open piece of paper, obviously air resistance in that case is pretty significant. But that's not really what we're focusing in on. The second reason that we're going to ignore air resistance is because, quite frankly, air resistance is incredibly complicated. All right, it depends on a whole host of factors from the density of the air, how fast the object is moving, what's its shape, et cetera, et cetera, et cetera. And mathematically, that becomes a real challenge for a student to try to model. All right, this is something that, people in college spend time studying who are, physics majors, and they work with pretty heavy duty mathematics to be able to do that. So it's not really appropriate for us to talk about it at that level in a high school physics class. All right, so if we're neglecting air resistance, then free fall is constantly accelerated motion in one dimension, meaning it's a uniform acceleration, a consistent acceleration in the downwards direction. Okay. When we're solving problems, we're going to think of it kind of like we would in the math class, right? So if we think of our x and y axes in math, we call the positive y axis upwards. So for that reason, we're going to call upwards direction the positive direction. So if that's true, and we already said that the acceleration is downwards because of gravity, then that means the acceleration is going to be written as a negative, and you'll notice I circled it here, negative 9.8 meters per second squared. The reason for the negative sign, folks, is because of the direction. It's pointing in a downwards direction. It's not, oh, well, that means it's slowing down or that means it's getting faster or whatever. You don't want to think about it like that. You want to think of it as the negative sign tells me it's this way and not this way. The direction of the acceleration is downward. And that's going to be universal for every falling object, assuming that we have no air resistance. Okay. You'll also notice I wrote here in purple, the kinematics equations are valid. So those kinematics equations that we learned about in our last lesson, we can use those in this scenario because it's a constantly accelerating object. So those equations are going to be valid here. Okay, so we saw in class that if we drop, let's say, a ball or a weight and a piece of paper, that they don't fall at the same rate normally. All right. And the reason is because there's air all around us, and the air really affects that paper in a stronger way than it does that other object. All right. But if we were able to take away that effect, and we talked about one way we could do that, would be to crumple up the paper. Another way to do that would be to do it in a vacuum where there's no air. If we are able to do that sort of thing, then we would see both objects falling at exactly the same rate. All right, so gravity causes the same acceleration on all objects. Okay, so let's recap with some key points. So first, if gravity is the only force acting on something, it's in free fall, regardless of which way it's moving. Whether it's on its way up, whether it's on its way back down, whether you've thrown it, doesn't matter. If gravity is the only force acting on it, it's in free fall. Second, because gravity is a constant force downward, it's the same amount of force downward on each object, it causes the object to have a uniform acceleration of 9.8 meters per second squared in the downwards direction. So gravity causes the same acceleration on all objects. Now I want to be careful about this. This is a point that isn't really super critical when we're talking about kinematics, but later on when we talk about Newton's laws, it will become so. So I'll just mention it here. What I'm not saying is that gravity exerts the same force on all objects. That's not a true statement. All right, gravity doesn't exert the same force on all things, but because the force it exerts doesn't change as the object moves, the acceleration that it will cause will be a consistent acceleration. And every object ends up with the same acceleration. We'll talk more about why when we get into Newton's laws. Next, the acceleration is always downwards. All right, and because we call it upward positive, then that means the acceleration is negative. The object might have a positive or negative velocity depending on which way it's headed. Remember, which way the object is actually moving tells us what its velocity is, not what its acceleration is. So if it's headed upwards, it's got a positive velocity. If it's headed downwards, it has a negative velocity. If it's at rest, it has zero velocity. But if it's in free fall, its acceleration is downward the whole time. The velocity of an object in free fall will consistently change since gravity is a constant force. So as the object travels up, it's going to be slowing down consistently. And then as the object comes back down, it's going to be speeding up consistently. Happens in a consistent basis because we have a constant force. All right. And then lastly, if the object is thrown upwards, it slows its velocity to zero at the peak, and then it becomes a negative velocity as it comes back down. All right, so the velocity goes from a positive value to zero when it stops to a negative velocity when it comes back down. That entire time, the acceleration is downwards at negative 9.8 meters per second squared. So I've probably said that about 100 times already, but the most important point, gravity causes a constant downwards acceleration of negative 9.8 meters per second squared.